so please give a warm welcome to Ines.
Yeah, hi everyone. Also, I'm really sorry for being late. I just heard I'm the reason that everything's delayed because I took too long scooting with the e-scooter over like the bridge and like looking at Heidelberg on the way because it's my first time in Heidelberg, and interestingly, the city still always had a very special place in my heart because it's where my parents met back in the 80s, I think, when my mom was studying Spanish at the University of Heidelberg, and my dad went to hotel school. So yeah,
so
always.
Without Heidelberg, no Ines. Right?
Yeah, exactly. Without Heidelberg, I wouldn't exist. So it's definitely a very special PyData, and I've always wanted to visit. So I'm really happy to be here. And yeah, so I will talk about large language models, which is a topic on everyone's mind. And maybe, is this working? Oh, come on. A quick intro. Some of you might know me for my work on SpaCy, which is an open source library for natural language processing in Python. We've been very lucky to have a lot of users, and we have been around for a long time. People seem to have liked the library. It's been downloaded over 160 million times. And SpaCy really focuses on real-world use cases and building pipelines that can be used in production. And it was designed like that from pretty much day one. And we've actually put a lot of work, maybe some people might say too much work, in really ensuring stability, not breaking backwards compatibility. But a really nice effect of that is that there's a lot of SpaCy code out there. The actual usage hasn't changed that much. And that means that ChatGPT is actually really good at writing SpaCy code, which is kind of like another meta level. Like instead of using ChatGPT to do things for you, you could use ChatGPT to generate rules that let SpaCy do something for you much faster and more efficiently. So that's all really cool. And another thing we do at Explosion is Prodigy, which is a modern annotation tool that's fully scriptable in Python and really helps developers create training data, create evaluation data for machine learning models, especially for any structured task, which is incredibly common in real-world applications. And yeah, Prodigy's also been quite popular. We currently have over 8,000 users, probably even more. And yeah, it's also similar to SpaCy. It's also really designed from the ground up to be used in real projects and also be used as a tool that fits neatly into your workflow, powered by Python, which makes it really easy to extend any library. And currently, we have been working on an extension that takes Prodigy into the cloud together with SpaCy, while also ensuring data privacy, scriptability. That's currently in beta. If that's something you're interested in, like creating data, working with data, really going end-to-end from an idea to a trained model, you can also talk to me about that because, yeah, we're ready to roll out our first big product soon. And yeah, here, oh yeah, we can see some of the Python that goes into Prodigy. And yeah, with all that in mind, before we kind of go deeper into large language models, what can they do, what does it all mean, I think to me, this is a really important distinction that we kind of need to make clear from the get-go, and that's the difference between generative and predictive tasks. So large language models, GPT, whatever, these models have introduced like a lot of new capabilities, especially on the generative side, which is stuff like summarization, reasoning, problem solving, paraphrasing, style transfer, question answering. And these are all really cool and super important, and also things we couldn't so easily do on that level before. And then on the other hand, there are also tasks where the output is not text to text, but where the output is more something that's machine readable instead of human readable. And that's what I call predictive tasks. And that's stuff like text classification, entity recognition, relation extraction, co-reference resolution, grammar, morphology, semantic parsing, discourse structure, everything where the output is some kind of structured format. And I don't have any exact statistics on that, but I would say that the absolute majority of all machine learning systems, NLP systems that are currently in use and especially already providing value are more on the predictive side, because it's often, often the output needs to be consumed by something else, feeds into some other process, and this is also an area where, larger models can help a lot, and they're surprisingly good at it, but also not as good yet as you might think from maybe, scrolling through your LinkedIn feed or talking to ChatGPT. So there's also still, a lot of room for improvement. And I also want to talk about, kind of a vision that goes beyond like, hey, let's just, talk to some bot, because we think that, hey, that's not ambitious enough. We can do so much. We can go further than that. But basically, generative and predictive, that's the distinction. And also, of course, a lot of the software we've been working on, it's really more on the predictive side, because there's a lot of really interesting stuff you can do there. So, the distinction again, human readable, machine readable. And if we're looking at what can these new models that we all have access to and that have these new capabilities, like what does it mean for the future? How does it all fit in? And what will it say about like our life and our work in, say, 5 to 10 years? One thing I always like to do is kind of go back and look at the history of how people thought about technology of the future, and exact cases where we know the answer, and maybe what we can learn from that and how we can use that to shape how we are thinking about the future. And my absolute favorite that I've already showed, I think, in many talks, so sorry if you've seen this before, are these postcards from the World Exhibition in 1900. And these show how people imagined the year 2000. And I think it's like, there are more of these. I love looking at them. It's like super interesting. And what you can really see here is that, like, yes, people try to solve problems that we have also solved, but also in inherently human-shaped ways, or by very directly solving the way these things were dealt with before, like this like scrubbing robot, or like this very physics-defying flying firefighter force that, like, I don't know, does not consider water pressure, but we have solved all of these things, and some of them actually, this vision there for video calls was actually relatively accurate, but we also went a step further, and we didn't just take the problem and translated it one-to-one into, a technical solution. Especially, for the firefighting, yes, we might have, built better fire trucks, but we also built smoke alarms, and we even built, we use better materials to build buildings that are not wood to prevent these fires in the first place. So, it goes a lot further than that. And similarly, even if we're looking at like, direct computers and technology replacing human labor, one thing we see here is, we have a whole room of people adding up things and calculating sums, and we can replace all of that with a calculator. And again, also one of my absolute favorites, up to the 1950s, the job of a knocker-upper existed, and those were people hired to walk around with a stick, knock on people's windows so they would wake up in time for work when alarm clocks weren't reliable enough. And yes, we have replaced this with technology, with better alarm clocks, with phones that we now have in our pockets. But I think this is also a great example. We did not replace knocker-uppers with a window knocking machine. And I think this is always a very important test if you're thinking about like, hey, how can I use technology to solve a problem? Am I building the alarm clock and really solving the problem in the most efficient way for the human? Or am I building a window knocking machine that literally translates what a human does into technology? And we can actually see an example of this in the more recent past, in the first kind of chatbot hype where people imagined, hey, we can finally build something that kind of works. Let's try and mimic exactly what a human does and translate that into a chatbot so you can talk to a bot to book your meetings. And a lot of that didn't work so well because it turned out that there are actually much better ways to use technology to solve that problem. And one of those is Calendly, which I love for scheduling. You send someone a link and they can book something. That's much better than talking to a bot version of a human going back and forth on time zones, or even using NLP and using language understanding in a slightly different way by, say, letting you write natural language descriptions of your appointments that are then automatically added to your calendar. And I think we also have a similar questions that we have to ask ourselves when we look at, hey, we have these large models that can do pretty impressive things and really add a lot of new capabilities. What does that mean? How will the future look like? And what's kind of the equivalent of, say, a window knocking machine versus an alarm clock? And when we look at NLP, natural language processing, in the age of large language models like GPT-4, ChatGPT, they're kind of two different, they're kind of, in a lot of ways, polar visions of how the future could look. And one of those is on this spectrum of, on the one side, structured data is still going to be really important. SQL, whatever databases, that's all you need. And that's going to kind of stay that way. And on the other end, you have a take that's more like, hey, dialogue is all you need. All problems are going to be solved by talking to a bot in a dialogue form, and we can cut out the whole database thing altogether. And similarly, on another axis, we have the one end of the spectrum. Well, we still need a lot of humans that can create data, that can work with the system, and really build these applications. And on the other end, you have a take that we also sometimes see that's, well, ultimately, it's all going to be about prompting. That's, the future, is, we prompt a model. We're not going to actually interact with it in any other way. And those are kind of the questions. And given that we've talked about generative and predictive tasks, here I wanted to show you like a very classic NLP problem that we see all the time that comes up in pretty much any industry. And that's also something kind of fundamental that, like, us humans, we've done before computers manually, and then we've been doing it with computers, and now we're trying to do it with better and better machine learning models. And that's extracting structured data from unstructured text. So, here we have a text about a fundraising announcement, and of course, these come in any kind of natural language, and what we want to find out is who invested in which company, how much money, and so on, put that in a database so we can later calculate stuff. So ultimately, what we really have to do here is we have to extract these companies, we have to disambiguate them, so like map them to an entry in a knowledge base, make sure that it's that Apple, that Hooli, and so on that we're talking about. We need to look it up in some custom database, like whether it's Crunchbase or some internal thing that like we've been curating for decades. And also currency, we need to extract that. After we've extracted that, we need to normalize that into like an integer that we can do maths with. And we also need to extract relations. So that's a very classic problem, and there are different ways to solve that. Like, there is, you can sometimes do some of these things quite well by just prompting a large language model. You can build it the old school way. But this is really the thing that we're trying to solve. And if we can do that better, that's kind of one of the things that has the biggest value in like a lot of real world applications. And, we're going back here, we're kind of we're on the predictive side. And one thing, we can see here is, well, we can, take something like GPT-4 out of the box, ask it to give us all of that information. Then it gives us back text because, it's generative. We're going back, trying to extract all the information out of it. That works quite well. But also, what if we kind of want more of this? And also, given that this is kind of my terminology slide as well, don't have this specifically on the slide, but I think one other important distinction is, what are we even calling a large language model? Like, unfortunately, right, especially at the moment, the terminology in, I don't know, the field or in the world in general is incredibly vague. And there's also, some PR speak involved. And, so you find people calling every fine-tuned BERT model that companies have had in production for like years a large language model now, which is maybe technically correct, but also technically not. So there is like, there is this distinction here. I'm mostly using LLM to mean like a model that does in-context learning, and I'm getting to that later, but we're not talking about stuff we've already had for a long time. But one thing that's actually kind of interesting and surprising is that at the moment, out of the box, large language models don't necessarily do that well on structured prediction tasks, at least not as well as you might think. So here are some benchmarks we ran, and you can see the accuracy of and the accuracy on the percent of examples that we use. So we basically compared what if we train like a bird-sized model and compare that against like just the zero-shot output that we get. And first one we did, that was a sentiment data set. That's a really relatively easy problem, predicting sentiment. And here what we can see is, well, almost 95% out of the box. That's really good. It's a simple problem. And here still we do need to use 50% of the examples that we have if we're really training a model on labeled examples where we know the answer to get to that baseline. But again, it's still, we can still beat that with only, 50% of the training set. So next one is slightly harder, but still pretty standard news data set predicting categories over news. And here we see that actually the baseline starts pretty low. I mean, 85% pretty good. We wouldn't have been able to do that so easily years ago. But even with 1% of the training data, we can beat that by 5%. So if we just take 1% of labeled examples, train a model with it, we have something that's much smaller and also much faster, private, and better. So that was like pretty exciting. So it's like, okay, can we do this even more? And here's an even harder data set, which is about banking. So lots of specific terminology, baseline. Still, again, 70% is not bad, but it's also quite low. We want better than that. And here again, with even with 5% of examples, we can beat that significantly, and it even keeps going up. So if we use the whole training set, or even just 50% of it, we can get significantly better accuracy. So that's all pretty motivating. So if we know exactly what we're trying to do, like predict categories, we can we can build something that's better pretty easily. And another nice example here is this is on named entity recognition. So extracting spans of texts like person, organization from unstructured data. So here what we can see is that that's the current state of the art, unless something came up recently, which I don't think it did. So this is on few-shot prompting. If we just take GPT-4, GPT 3.5, we get pretty good accuracy out of the box on this benchmark data set. Also, still lower than what's out there and easy to use, and also still lower, interestingly, than the state of the art in 2003, which is when that data set was released. And granted, this is just like this is one benchmark data set that's not even that great, and also we shouldn't discount that the big advantage here is that, like, hey, we can get to 83% accuracy without doing anything, but we can also get much higher. And I think that's kind of where the interesting part is. If we can get a lot of nice things out of the box, how much further can we bring this? And again here, the important distinction, whether we call it LLM or however we call it, is that these large models, they use in-context learning. So they know a lot about what the text means, but they don't really know what you want it to do, which is, which makes a lot of sense. And then on the other side, we have what I'm calling task-specific models, which for some reason also some people call LLMs, which makes the whole thing really confusing. And here we're really talking about fine-tuning something like BERT for a very specific task. If we know what we want, we can take advantage of that. So here, a model obviously knows a lot less about what the text means because it's smaller, but we can used to our advantage that we can encode exactly what we wanted to do in the model. And that means that we can actually use this during development, and we can take this large language model, take everything that's in it that's good and useful, and then use that to develop a task-specific model that has a lot of advantages. It's smaller, faster, better, and we can really, as we've seen, even on some pretty basic experiments, we can beat the accuracy, and I'm sure with better larger language models and better techniques, we can take this even further and make this even more efficient. So what we, as the developer, have to do here is prompt engineering. We have to still think about how do we define the problem. That's not, that's not going to go away magically if, we still have to decide what we even want to do and why and how. We have to create some data. We can use the large language model to do that, but we still have to, make sure that our data is good, because otherwise we can't fine-tune a model that's like this good. And we, of course, need to train it and evaluate it. Evaluation we need to do in any case, because we need to know how good our system is and if it improves. And it's easy to have a system that's 100% accurate if your evaluation is shit. But that's not the point. We want to build something that's actually good. And then this task-specific model is something we can actually ship to production. And it's something we own, runs, can be under 1 gigabyte, and it just can run fast, efficient. As we've also seen previously in the benchmarks, any task-specific model will be significantly faster than any API. We don't have to worry about latency. We can just ship it. And so what I'm basically saying is, if we go back to our axes here, I see modern practical NLP pretty much in the middle of this. We still want structured data. There are a lot of use cases and problems where, kind of replacing that with a dialogue would be the equivalent of a window knocking machine. Like, structured data has its place and it's good for a lot of things. We still need humans in the loop. We need high quality data. We need to evaluate whether what we're doing makes sense and has the right purpose. And often the end consumer of this are humans. So we need subject matter experts who can actually validate what we're doing. But the prompting and dialogue-based generative models do give us very fast prototyping. So instead of having to collect hundreds of examples or putting in 40 hours before we get kind of a shit model we can improve, we can now start off with like a pretty decent or even kind of shit model that we can improve and use the LLMs or the prompting at development time to build a system that's even better than what we could do before. And I also think it's going to be powered by open source, of course, on the code side, but also a lot of the work, and especially in academia, is also still happening in the commons and is public. And I do think open source technologies, open source tooling, and of course Python will play a big role in that. And we also need a mix of conversational and graphical interfaces. Like, just because you can talk to this model in a conversational style doesn't mean that a conversational UI is like the best solution for everything. Again, window knocking machines versus alarm clocks. So in a lot of cases, a graphical UI where you can click a button or select a meeting you want to book or do whatever, if you're an analyst, looking at a list of things you can filter is better than having to talk to a bot. So I think, none of this graphical interfaces are not going away, and that means we also need structured data, and we need to approach this in a more holistic way. So in practice, I'll give you like a very quick, I know, I've started late, so of course I'm late. But I want to give you a little example of what this looks like in practice, what you can already use now, and also, of course, a little snapshot of what we've been developing. So what we really see as incredibly important in this is a large language model powered collaborative data development platform and environment that developers can work on, subject matter experts can work on, and where you can use the LLMs to create labeled data that you can then use to train better models. And that means if you want to train these better task-specific models, that data needs to be good. Transfer learning has this great advantage that we can train really good models with good embeddings and very few examples, but that actually makes these very few examples more valuable, not less. So these need to be really good, but with good tooling, we can do that. And we also want to tune prompts and compare the models in an empirical way. And there's like a lot of cool work happening in that. We also have been doing some of that internally. Like a lot of the things people do are mostly trial and error and just like trying something out and saying, this feels slightly better. But you know, you want to have an easy way to just see what works best. And with all of that, you can build data sets and actually train and also evaluate more efficient production-ready pipelines that really solve the problem that you have and come with all the other advantages. So here's an example actually of some of the workflows we've built in our annotation tool Prodigy, but something similar you know, works even, you know, if you can even build something like that yourself on the command line in just Python. And what we're doing here is we ask the OpenAI API for predictions on this text given these labels, and then we highlight those spans in the text. All the model has seen are the labels, now also optional label descriptions and the text. And then it tries to give us these spans. What we can see is there are some mistakes. It will always inevitably make mistakes, especially it can be quite inconsistent and also non-deterministic. So, you know, you might do the same thing tomorrow and it gives you different predictions, which kind of sucks. But you can correct these mistakes, yeah, and submit it. So that's all very easy. And you can also add correct answers to the prompt to tune it. If you have like specific things where you feel like, hey, the model keeps making mistakes, so it's something weird in my domain, you can include it in the prompt and hopefully get better predictions, or not, and then you kind of have to go back and include more examples. And under the hood there, one of the hard parts is that a generative model is generative, and so the output is text. So we feed it a text and we want structured data out of it, but what it gives us back is a text. So there's actually a lot of work going into like how can we write better prompts to achieve that and make it output something that like then lets us turn it back into structured annotations on the data, because again, it will just reply with this string location : London, Berlin, and then we kind of have to go and map that back in a text so we can say, hey, this character to this character, that's what we're interested in, because we really want to usually map it back into our original data. And for that, we have built an extension to SpaCy, which is called SpaCy LLM, and it does take care of all of that, the prompting under the hood. In a way, it works quite similarly to what SpaCy does if you've used it before, because our vision has always been we want to build one named entity recognition component that just works and does the thing. You don't have to choose between lots of algorithms. It just works. And here we kind of trying to do the same thing with the prompting, and what you get back is a doc object that works just like any other SpaCy doc object, whether you use a machine learning model, whether you use rules, or whether you use any large language model, whether it's an API, but also an open source model you host yourself, someone else hosts under the hood. So you can easily swap that out and compare the results as well, evaluate, get a score, know what baseline you have to beat, and then take it from there. And so, yep, currently these are components that we have, including really cool stuff that actually was a lot harder to do previously with just a machine learning model, like relation extraction. That can work quite well, so we've been trying this out, and that's actually quite exciting, but also even for more classic linguistic tasks like lemmatization. That's also still incredibly important in a lot of applications, not as sexy as a lot of other things, but still pretty important, and you can use under the hood either a large language model, a supervised model, or rules, and you can mix and match these as well in a pipeline, so you can have one component powered by that, one component powered by that, and that's kind of the concept of it, and it's under very active development. We've been continuously adding features, and we think this could really be a big part in that vision that we have that allows people to build these kind of superior models, basically. So to wrap this up and have barbecue, my main point that I'm trying to make here is that easier isn't ambitious enough. Yes, a lot of advantages of just writing a prompt are that it's easy and helps people get started. And that's great. And I think this will have a huge positive impact on our field. But we also want to think beyond just, hey, let's put some API in our system and call it a day. We don't want to build stuff that's actually worse than what we're currently building. And the quality of the systems, the machine learning systems that are in production today is high. And we shouldn't underestimate that. So we don't want to build systems and things that are worse just because, oh, it's a bit easier, or maybe it's a bit cheaper, or maybe not. So my main goal or my main message is be more ambitious. And that's because, well, often being specific is better. If you know what you want, you can build systems that do exactly what you want to do. And last time I gave a talk, or this talk, in a slightly modified version, I got a question asking me about like Skynet and like, oh, apocalypse, and like, oh, if I believe in like machines taking over and the whole Duma argument. And actually, even aside from anything I said in this talk today, if you are worried about like all the Duma outcomes, you should also care about this, because if you train a task-specific fine-tuned bird, this is never going to take over the world. Like, this is going to predict 1 out of 5 labels, and no matter what you give it, it's never going to be able to do something evil. Like, I'm not a Duma, but like, if you meet Dumas, this is also the message for you. And also, smaller and faster is better. There's so many, we don't need to run a thing, like we have good systems in production. We don't need to replace them with like an API that runs at 100 words per second. Like, there are a lot of cases where we want something small and we want something fast and we want something that we can maybe run on a phone, on one single GPU, on your laptop, even if it's not the latest M2 MacBook. And there's absolutely a case for that. And why would we not do that if we can? Like, if we can make models bigger, we can also make them smaller while making them just as good and much better at the very specific task that we know we want. And private is also better. Like, we don't have to send our data to some random API in some random country or some random startup, and we shouldn't have to settle for that. We can run things ourselves, whether we care about data privacy, whether we're forced to do this by law or not. Data privacy is good, and I think that's another great advantage. And finally, better is always better. Like, we want to train systems that are better than what we have, not worse. There are a lot of cases where it's always going to be a race to the top. We don't want a fraud detection system that's like surprisingly good given it hasn't been trained. Like, it needs to be like really good and better than anything else. And there are tons of these use cases. So I think we should aim higher than just, it's pretty good and convenient. And I think there's a lot to be done. There's also a lot we're working on, and I think we can be more ambitious. And yeah, I'm very excited to see what the future holds. Thanks. Are we doing questions now?
Yes. Schon on? Switch on. Test us? Yes. All right, we do have a few minutes for questions, only a few, because barbecue is waiting already.
But we can do barbecue and people can just, I don't want people to sit here like,
we'll do a quick one, okay?
Okay.
So you can ask a question on Slido or here in the room. If you want to ask a question here in the room, just raise your hand and I'll forward you the microphone, and I'll do my best with my climbing abilities here. Okay, any question in the room? Okay, there's one. Could you pass it straight to the back?
Hey, thank you for the nice talk. You showed a prompt that makes give you lines of the named entities.
Yeah.
But you could maybe also have told it, hey, give me a JSON structured output and give me also all the structured data that I want. I assume you tried that and it's not great, but do you think it will always not be great?
Yeah, so this is a good question. Also, it reminded me that the prompt I have on this slide is sort of the bad prompt, like not the best prompt, not the current prompt, because we have actually, so in the latest version of SpaCy, we implemented, let me go through here. I almost had it, sorry. Wait, where's my, yeah, here. That paper, which is the state-of-the-art on few shop prompting, and that implements a technique that is better than pretty much anything else people have tried for NER, and that's what we're implementing. I think it's not the JSON way of doing it, and I do think there are some cases where the JSON works, but also in our case, there are a lot of, we don't need to predict the whole structure. There's a lot we can infer once we kind of know where to align it in the text. So I don't exactly know all the things we've tried, but basically what we have implemented now is something that's better. And yeah, you can, so there's a reference to the paper here. It's also in SpaCy LLM. I can look at this later and then maybe give you some more background on that. But yeah, this is this is kind of the prompt engineering, magic, stuff that everyone's playing around with, and it's actually, people present it like it's a science, when actually I think a lot of it is just man, we all don't really know what's going on, and people are just trying.
All right, so questions on Slido are more targeted to the panel later, so maybe another question in the room, and then we'll go for barbecue. Oh, maybe I shouldn't have said that, sorry, but is there another question? Yep.
Yeah. A question about another layer of entity recognition, so to say, to differentiate a relation, for example, as absurd or fictitious or factual. Is there something that you think is going into that direction with the use, for example, of knowledge graphs, or because you're already building some kind of information relations between different entities that you can actually go to a database and check, okay, is this factual or is this fictitious or is this actually absurd?
Yeah, so that's a good question, and actually that also, I brought up this slide because it kind of ties into this pipeline design and really the problem of, hey, I have this thing which I want, how do I break it down into something that works best? And I think one option, it sounds like knowledge-based entity linking, something like that sounds like, that is, for example, a component you can add. So even if you do NER with the LLM, SpaCy, for example, has a knowledge base component that you can plug in. You can also, write something custom. And then there's an interesting question, if you have mentions that you extract as spans, is that you could benchmark that against an approach where you actually just do it simpler as a text classification task. So you're given this sentence with these entity mentions, are these absurd or something? And that is that's kind of a classic reimagining or breaking the task down into something that's potentially easier, and that's kind of the thing you need to try out, and that's also where we come in and say, hey, if we try to build tools that make this easier and make it easier to experiment and try out these different approaches. And
I was thinking, so the use case would be typically if you're in a company, you have a customer, and then he writes you something, and maybe you need your model or your recommendation to actually give better recommendation, but you need actually to ask further because maybe the customer didn't understand exactly what he was expressing in terms of business language, for example. You would ask, what's the problem? I didn't understand this problem because actually maybe I'm confused. Maybe is this thing what you meant?
Yeah, or you could use, maybe if you have, depending on what you predict, if that gives you confidence scores and you want to be extra sure, you could say okay, if my model gives me less than 80%, I need to ask the user to rephrase. Or I could use a generative model to rephrase it, ask the user back, is this what you meant? And then the user can say yes or no, or there are a lot of these combinations. But again, also I think that's where you still need to break down the problem and reason about the different flows. Yeah.
Thank you.
All right, so Ines will be around
Yeah.
for the barbecue, and I'm sure she will take all your questions there. And also she will be around for the panel later, right?
Yeah.
So I suggest we go for barbecue now. And to those watching remotely, see you later. We're about half an hour delayed, so we'll start about half an hour late.
Sorry, my fault.